All right. So last week we started looking at probabilities and how to find those and how to find the percentages and how to do all that wonderful stuff with it. Now we're going to start looking at how we can start doing the basics of statistics with probabilities. So remember when we go back to, we looked at in chapters 1 through 4, we were talking about like standard deviation and variance and mean and those type of things. We still can do that stuff with probability. And that's what we're going to start looking at today. So there are two different types of probability distributions. There are discrete ones and continuous ones. We're going to look at discrete this week, and we'll look at continuous next week. All right, so before we actually go through a couple of quick definitions. A random variable is the numerical outcome of a random process. So in essence, if we're looking back to what we were talking about before, a random variable is just an outcome. It's the pieces in that sample space. It's what are the options that I'm going to get. A probability distribution is a model that describes that random process. So we're going to, so a probability distribution is how often is each thing going to happen. Now, what's the difference between discrete and continuous? We talked about this before. Yes.
Continuous is including like all the information in between the points. So
yep.
Like temperature. Discrete is more jumping.
Yeah. So discrete are individual values. Continuous is going on basically everything. So if we're talking about a probability distribution that describes that, it's going to be a lot easier for us to work with one that's discrete because we can find the probability of each of those values as compared to a continuous one where it's constantly changing. So like a die, I can easily tell you each one of those is going to come up 1/6. That makes a lot of sense. Cards, 1 out of 52. That, again, makes sense. But how often does the temperature 62.35 degrees come up? That'd be a lot more complicated to figure out. So that's why next week we're going to look at those. Those probability distributions are going to be a little more complicated. But we're going to start off with the easy ones first. All right, a discrete random variable. When we're describing a discrete random variable, we should be able to state the variable, what we're looking at, list all possible values of the variable, and determine the probabilities for each of those values. Now, sometimes 2 and 3 does not necessarily have to be completely written out. You can describe it using words instead of actually listing every single possible value. But it should be possible to do that if it's a discrete variable. And then each of those values has a specific probability that is attached to it. Again, the more realistic the situation, the more complicated that's going to end up being. But we should still be able to do it. We're going to look at a few of those cases. Chance to finish writing that down, and then we'll look at it. All right. That's what happens when I do it on my computer at home instead of my laptop. They don't always fit. All right. So my random phenomenon, or my random process, I'm going to toss a die and observe the outcome of the toss. So the first thing we should be able to do is identify the random variable. So X, so just like in algebra, we can use variables for this, is the outcome of the toss of the die. So what are the values that I would get when I roll a die? Yes, 1, 2, 3, 4, 5, 6. So we can easily identify each of those values. So the value of X is 1 through 6. So sometimes you'll actually see this instead of listed as the value of X. You'll see this as X equals, and you'll see this as X equals X. So in this case, a die is very simple. Each one, when you roll it, has an equal chance of coming up. They would all have a 1/6 chance of coming up. So that's how you would describe a discrete random variable. So the first one is just X equals. This one is the probability that X equals would be 1 is this one. So when you're looking at it, it'd be like this: X equals 1. And this is the probability of X equals 2, and this would be the probability of X equals 6. So that's how they actually write it a lot of times. Again, it's not as important to know the actual, like, the way it's written. It's more important to understand what to do with it. So, but you will see those, and I want to make sure you understand what they mean. All right, so let's look at a couple more realistic ones. So the number of defective integrated circuits received in a batch of 1,000. So is this a discrete or a continuous situation? Discrete, because we can't have 1.5 integrated circuits broken. It'd be 1 or 2 or 3. So in that situation, it is discrete. So the number of defective integrated circuits would be anything from 0 to 1,000. So notice how, unlike the last one where they listed out 1, 2, 3, 4, 5, 6, this one they're just describing it in words. That's a completely okay way to do it. So you don't necessarily have to say x1 equals 0, x2, and like nx, those type of things, but the actual integers between 0 and 1,000 inclusively, that's completely acceptable. Where it says probability distribution unknown, is that okay? Well, in this situation, it's fine, we don't know it. However, if you were going to actually do this, you would have to actually come up with some information or data based on that. To do that, they'd have to go back and look at historical data for each of the boxes. So they'd have to go through and look and do some kind of study to determine how often those things occur. So there obviously is a probability distribution for this. They would come up at a certain number of times. It's not going to be as simple as a die where everyone comes up the exact same times. Like 0 things isn't going to be 1 out of every 1,000, 1 out is going to be 1 out of every 1,000 boxes, and those type of things. So we don't necessarily know exactly what the distribution is, but we know there is one. So the head nurse of a pediatric division at Sister Mercy Hospital is determining the capacity requirement for a nursery. So my random variable is the number of babies born at the hospital each day. Is that discrete or continuous? Discrete. Yes, we'd either have 1 kid, 2 kids, 3 kids. We're not putting kids in pieces. The range of values would be 0 to some large number. Like we don't necessarily know the max that it was going to end up being, right? So that's like, unlike the last one where we said, okay, it's 0 to 1,000, this one it's 0 to some number. Okay. And again, the probability distribution would be unknown. We don't know exactly what's going to happen. However, I'm sure the hospital has been around for a while, so we probably could look back over time and be able to come up with a decent probability distribution for it. But we would need that data. Local restaurant has expressed a policy that states lunch will be served within 15 minutes of ordering or it will be free. Obviously, the restaurant is keen about not giving away the food, but the length of time to prepare each meal varies because of the difference in the preparation time of each dish, low in the kitchen, about all these type of things. So in this case, what's the variable? What's the thing that we don't know at the end? Yeah, that's that time thing, right? So there's lots of things that can go into why that time exists, but the variable that I'm concerned with is time. Is this discrete or continuous? This is continuous. So in this case, 0 to, I probably wouldn't necessarily put infinity. Technically, it could go to infinity, but in this type of a real life situation, I probably would cap it. It's like, I'm pretty sure if you're going to tell me that the lunch is taking a couple hours, I'm walking out the door. I'm probably not going to stand around and wait for it. Even if you're giving it to me for free, I'm probably not going to wait for it. So, yes.
I don't know, maybe this is just being pedantic, but wouldn't time stop eventually?
Well, yes, time would also stop eventually. This is where the vision of what infinity is and the actual reality of what infinity is two completely different things. Now, the probability distribution for this, we probably could look at it with some historical data to be able to determine, okay, like this is how many food is done in a minute, this is how much food is done in 2 minutes, but that continuous nature of it might make it a lot more complicated to determine. Okay, because like every meal is going to be a different time limit. It's like, okay, 1 minute 32 seconds, 1 minute 40 seconds, those type of things would be a little more complicated to figure out. Do you know how I know this is actually used quite often in every restaurant nowadays? How many times have you ever gone to a fast food restaurant and they told you to pull forward after you got your food and they didn't hand you your food and told you to go sit in a parking spot and wait? And it's because there's a sensor in the ground that tells how long that car has been there. And they don't want their timers to go over a certain number. Yeah. Yep. The worst ones is when they make you pull forward and then back up. It's like, it annoys me. I understand why they're doing it, but it annoys me. It's all about metrics and numbers and stuff like that at that point. All right. So the first thing we're looking at, let's see, which ones are these discrete, which ones are continuous? The total points scored in a football game for a local high school, discrete or continuous? Discrete. The daily price of a stock. It's money, so it's most likely it's going to be continuous in that respect. The interest rate charged by local banks for a 30-year mortgage. Continuous as well. The number of times a backup of computer network is performed in a month. Discrete. The amount of sugar imported by the U.S. in a day.
Great. I'd say
Discrete
continuous.
or continuous?
I'd say continuous.
You can have like a pound and a half imported.
Yeah.
So,
Well, it depends on how we're measuring it. That's
Right.
the thing.
but it's still a weight, right?
Yes.
So, and weight and typically is a continuous piece of information. Okay. And so it's probably in tons, but it's still weight. Yes.
Unless we're, well, it would be weight. It would more likely be weight, but I guess technically we can also measure it by like packages.
Yeah. I'm gonna assume, because it doesn't qualify here, I'm gonna assume it's by weight than in terms of packaging. And so because packaging can vary. So like depending on the packaging you're getting, that would then change how it'd be looked at. So I'm gonna go with weight because that's the more standardized thing, which in this case I would say is continuous. But you can now see how this is section 7.1. And we're now done with 7.1 actually, but you can now see how Hawks is going to screw you up when they ask you your questions in the program. Because these are the types of questions they're going to ask you. Is it discrete or continuous? All right. Let's look at actually creating a probability distribution. What are two of the criteria when we look back at probability last week? What were two of the laws that we had? One of them that was the probability had to add up to 1, right? If you add up all the probabilities, they have to equal 1. And the probability of any value has to be between 0 and 1. So 0 means it never happens, 1 means it always happens. But those were the same rules are going to apply to this when we're looking at that distribution. Since we're looking at a group of values, you're probably not going to have zeros and ones in there. You're probably going to have numbers, but it could happen. Look at flipping a coin. I did this on my desktop this morning, and my desktop screen's bigger. All right. Consider the random phenomenon of tossing a coin 3 times and counting the number of heads. So in this case, what my values of x's, how many heads could I possibly have? I could have 3, I could have 2, I could have 1, and I could have none, right? Those are all possible outcomes of the number of heads. Now, this over here, remember we did that list last week? We did up the number of tails, heads, and stuff like that. And they just counted it. So the probability of getting no heads is 1/8. 1 head is 3/8, 2 heads is 3/8, and 3 heads is 1/8. If you add all those up, what do you get? 8 out of 8, which is 1. So it is a valid probability distribution for this. Okay. So x, and now you notice that you see that p x equals x values there. That's where those simple comes up. A lot of times you don't necessarily have to write down all the simple events. It just makes sense when you're flipping head or coins to write them down, so you can actually get the right amount of values there. All right. Let's look at one that does not have to do with coins. So this guy's a computer salesman. He's kept records on his computer sales for the last 200 days. The number of sales is 0, 1, 2, 3, and 4. So is this a discrete distribution? Or yes, because obviously you can't sell 1.5 computers. What's the most computers he's ever sold in a day? 4. So that was 0 through 4. So the most he's ever sold was 4. And he sold that in how many days? 40 days out of 200. So if I wanted to find the probability that he sold 4 computers, how would I do that?
By 40 by 200.
Correct. Okay, so I've got my frequency table here. So, but let's make our distribution. So I would do 40 divided by 200, which is what? You can give it to me as a decimal. Okay. Then I would do 20 divided by 200. What? So, is this a probability distribution valid? Is it a valid probability distribution? Does it add up to 1? Yes. 0.2, 0.1, 3 plus 3 is 6, plus 4, 2 is 8, 2 is 10. So 1. So it adds up to 1. Good. What's the probability that he will sell at least 2 computers each day? How do we figure that out? Sure. Nobody else wants to talk.
Yeah, I waited. 30% chance.
Wrong.
Oh.
English fooled him. Says, what's the probability that he will sell at least 2 computers each day? Yeah. Yeah. You're adding up to 2, the 3, and the 4. Okay. I only said it was wrong because of you. I didn't go through because I it's like so remember, reading is very, very important. Because if it was just 2 a day, that's right, 30%. It says at least 2, we're adding up the 2, the 3, and the 4. What's the probability that he will sell at most 2 computers each day? So at most would be what? 0, 1, and 2. So that would be 60%. If you added those 2 together, you're going to get over 1 because they are not mutually exclusive. They overlap. The 2 is in both of them. Okay. So at least means 2 or more. If it's a greater than 2, I would have only been looking at 3 and 4. So the wording really, really matters in these. Okay. All right. So as investors decided to purchase stock if there's at least a 50% chance that the stock price will be more than $32 in 30 days. Assuming the price of the stock 30 days from now is described in the table below. Yes, this is completely fictitious because you wouldn't have any specific probability for each of these. Should the investor purchase the stock? So what is the probability that the price of the stock will be more than $32 in 30 days? So in this case, we're adding up the 32.5 and the 33, right? So it would be 20%.
That one price of just 32 doesn't count.
It would have if it said 32 or more. But since it says more than 32, $32 isn't more than 32. So this is where, again, those words really matter. Actually, in this situation, even if you added the 32, it wouldn't have changed your actual answer to this question. Because the question says, is there at least a 50% chance that it'll be greater than? Even if you added the 20 in that situation, it'd be 40%. So it'd still be below the 50. But it's only the 15 or only the 32.5 and the 33 in the situation. Now, this is a really horrible graph because first of all, is stock prices a discrete probability or a continuous probability? It is continuous. And there's no way they're predicting the probability of each of those prices over the next 30 days like that. That is just not happening. All right. So the next thing we're going to look at is what's known as expected value. So whenever you play a game, any game, the expected value is what you would expect to win if you played that game, or how much you'd expect to get. The other way to look at it is it's also the mean or the average of those values. Okay. Now, if I go back and I look at, say, this chart here, I don't have a list of 30s and a list of 30s.5s. This type of table, if we go back to what we looked at mean with, is what type of mean? When we found mean, there was a few different ways we found mean. We had mean, we had trimmed mean, which is when I cut off some values, right? And what was the other one? Starts with a W. Weighted mean. So weighted mean, remember we looked at for like grades and stuff like that to figure out where you take the two values and you multiply them? That's in essence what we're going to do here. Okay. So the expected value is the sum of when you multiply the value times what the probability is. Okay. Once you multiply that, you add those all up, and that's going to be your expected value. So let's see if I have. Yeah, that's the first one. So let's go back up here, and we're going to take this. So I already figured these out. If I remember right, I'll make sure. Yep. All right. So if we're going to take each of these and we're going to multiply them together, so what's 0 times 0.2? 1 point times 0.1? 2 times 0.3? 3 times 0.2? And 4 times 0.8? Or 4.8, yeah. There we go. Add them all together. What do we get? 2.1. So on average, you would expect to sell 2.1 computers a day. That's the expected value. If you look at the probabilities in those numbers, does 2.1 make sense? Where's the middle? Where would be the median of these values? 2, right? Because that's where the 3 is, the biggest part right in the middle. So 2 would be the mode in this situation. That's one that's going to happen the most often. But that 50%, so I got 2 plus 1 plus 2, 3 is 60. That 50% somewhere in the middle there in the 2s. So that'd be my median. Question is, now remember, mean can be skewed, right? Mean gets pulled one direction or the other based on the values. Where are more of the values? Is it above 2 or below 2? Above. I got 40% over here and 30% over here, right? So I'd expect my mean to be pulled a little further this way. So 2.1 makes sense. Okay. Obviously, he's not going to sell 0.1 computers, but remember, average isn't always necessarily going to be exactly what you're going to sell. That's what you'd expect to sell. So most days he's going to sell 2 with an occasional 3 day in there on average. Does that process make sense? Okay. And they just did the same thing here. That's just the expected value. Now, this can be complicated to figure out and do all up by hand, especially if there's a lot of values. So I have an option for you. And I just linked this on my website too. So, and I looked, Ruguru doesn't have this, so we're gonna use this. There's a website called Statology that actually has all these stats calculators, and one of them is known as the probability distribution calculator. Statology. It is also, if you go to my website, I actually linked it there and posted it, so you can click right on that link there. I'll add the videos for today's classes after when I get home. So in this probability distribution calculator, you're going to type the probability and the value of that probability happening. So let's look at these two investment options. So I'm investing a certain amount of money. My profit for option A, I have the 20% probability of losing $2,000. I have a 10% probability of gaining nothing, a 30% probability of gaining 1,000, a 30% probability of gaining 2,000, and a 10% probability of gaining 4,000. So that's option A. Option B you see over there as well. So the question is what is the expected value of these two? Which one would be the better option to go with? If you're going to look at these two right now, which option would you go with? If you want option A, raise your hand. If you want option B, raise your hand. If you didn't raise your hand, you failed the class, you can leave now. No. Pick one. Look at the numbers and decide. Choose which way you want to go. Okay.
I would go with A.
So, now let's think about what things we looked at in chapters 1 through 4, right? We have options that we can start to look at determining which one's going to be better, right? Those things we looked at was mean or median, depending on the data. This one we're going to look at mean. What are some of the other things? What's the other thing that we looked at to help us figure out how data was shown? I'm specifically not using a one word. There was another calculation that we did to help us with data. Yeah. Yeah, we did standard deviation. What's that supposed to tell me? Yes.
Like how far the value is spread.
Yeah, it's spread, right? So the bigger the standard deviation, the more variance it is, the more spread out the data is. Okay, so in this situation, the bigger the standard deviation, the more risk that would be involved, right? I could get a really big payout, but I also can get a really low payout. All right. So if we're looking at these two, which one do you think would have the higher standard deviation? A or B? B, because we got that bigger spread, right? We're going down 3,000 and up to 4,000. 2,000 to 4,000. So the bigger spread looks like it's over here. But let's find out. Let's actually do it. So we're going to use Statology calculator. So all I'm going to do so you type in the probabilities. So I was there, my first one, I'm looking at both screens so you can see it, so I can see them. So I type in the actual percent and then the value. And then I calculate down the bottom. And there's my answer. So my mean is 900. My standard deviation is 1,757.8. So in this respect, what does mean represent? So mean tells you what your expected value is. Yeah, so the mean is if you did this long enough, you'd expect to make a profit about $900. Then you'd be losing money, yeah. It doesn't tell me how much I'm putting in because in this respect, it's just looking at profit. So it doesn't really matter how much you put in. So in this case, you expect to earn about a profit about $900. All right, let's do the other one. So if we look at the other one, we have a mean of 1400, a standard deviation of 2,576. So if I did this long enough, I would expect to make a profit of $1,400. But my standard deviation is 2,576. So my standard deviation is much higher. So there's more risk, more variance in that situation. Does that make sense? Yes.
So like for you personally, would you say is the better option?
Depends on how old you are. Because there was a very specific thing I said when I looked at the mean. Anybody catch the wording? Right. So expected value really looks at how the longer you do it, the closer it gets to that mean. If you are older, say you're in your 50s and you're investing, I don't have as long of a term to go to reach that possibility. So you want to do less risk, which would be a lower standard deviation. If you're younger, you have a lot longer to invest in, more risk is okay. So if you are 16, 17, 18 years old, getting your first job, start throwing some money aside and invest it. $1,000. So the economist in the classroom probably going to take issue with my very simplistic respect to this. If you put $1,000 in the stock market at 20 years old, okay, and let's say you get a 7% interest rate, you're basically going to double every 10 years, approximately. It's the rule of 72. All right, so approximately every 10 years, it's going to double. So if you put $1,000 in at the age of 20, at 30, you have $2,000. If you don't touch it, like this is the key, you don't touch it. So at 20, you have 1,000. At 30, you have 2,000. At 40, you have how much? 4,000. It doubles. At 50, you have 8,000. At 60, you have 16,000. So in 40 years, you went from $1,000 to $16,000. Okay.
I'm not buying a house.
You're right. But you only put away $1,000 and you did it once, right? Let's say you put away $100 every single week. Okay. You just put away $5,000 over the course of that year. If you did now doubled that $5,000 times 16. Hold on. So now you're at $160,000. If you did that every year, every single year, you'd be able to draw $160,000 at 60 years old. Very simplistic. Very simplistic on purpose. There's lots of other variables that go into this, including inflation and all this other stuff. But very simplistic. The concept is if you the big piece to this is if instead of doing it at 20, you started doing it at 30, you lose one of those doublings. So now instead of $16,000 at the end at 60, you only have $8,000 to 60. That's the biggest difference. Yes.
That's also effectively with Social Security. I mean, it's not the same. I mean, it's not
Should it? Yes.
again, going with the simple.
Should it?
Yeah.
Absolutely. Absolutely. That's the concept of Social Security. It is supposed you're putting money in, it should be invested. The money should be there when you retire. The problem is the government never actually invests the money.
No.
They use it immediately. So it's not there. That's the big difference between Social Security and like a 401k or a 403 or an IRA, things that you have control over. You're typically investing them and doing that. But that's the reason why I said, depending on how old you are, depends on how you want to do it. Because if you're younger, that doubling is really going to work into an effect for you. And more often it's going to be there. If you're older, you don't have as long to be able to double that. So you have to figure out ways to minimize your risks. So you don't lose possibility in the short term. So yes, very simplistic case. The rule of 72 actually does work though. That's actually how the mathematically proven to actually work. Problem is you don't typically get a standard interest rate that never changes. And there's other things that go into, like, the money today is worth less than it was 20, 30 years ago. So you think, oh, I have $160,000 today in today's money. Yes, but in 40 years, $160,000 might really only be like $50,000 today. So you got to look at those type of concepts as well. All right, but an easier way. So this is one way to look at it. But let's look at playing a game, a very simple game. Okay.
Thank you.
Yes, right there. So we're gonna roll a die. Okay. So what are the things I can get on a die? I can get 1 through 6, right? Actually, I have one here, so I'm just gonna snag the one back here. Oh, did I not? Yes, there it is. Let's use this. Okay. All right, so let's see. It costs you $10 to roll the die. If it comes up to be let's see, 0. Actually, no. All right. So that's how much money you're going to get if it hits those. Okay? Should you play this game? Why?
I'm not playing any game.
Right.
Probably not.
I'm not allowed to gamble. For religious reasons.
All right. So you said a very specific thing when you said it. I'm not playing any game where I'm going to lose money. Okay? So the question is, are you going to lose money?
I got a 1 out of 6.
Okay. So what are we looking at? What is the mathematical thing that we should look at to determine if I'm actually going to lose money over time? That's expected value. Expected value is what's going to give me that number. Okay. So let's find the expected value for this game. Yeah, we're going to multiply. Actually, we're going to multiply this times the money. So it's 1/6 times -20, 1/6 times 0, those things. All right. So what's 1/6 times -20? These two are easy. Those are 0. Okay. And then that would be positive 3.33. 10 times 0.6? It's 167. And 5 times 0.6. Or 50 times 0.6. Or 1/6. 50 times 1/6. What is it? All right, 8.33. All right, let's add these all up. What do I get? So, damn. I made this completely up on top of my head. I did not expect to come out to be exactly 10. So in this game, you would expect to basically break even. You play this game enough, you're winning no money, I'm winning no money. Okay? You could win $50, but you could lose $20. You could win $20, you could win $10, you could win nothing. The expected value for this game is exactly $10. So, is this a good casino game or is this a good gambling game? No. Why? Right? The company's not making any money. Okay. So, if I designed this game, it was a bad game for me. It's actually not a great game for you either. So, the way that this game is designed, I'm not making any money. You're not really going to make any money. Now, if I want to design a game that would, if I want to design a game, I want to make sure I'm making money, right? So I would want to make it less than $10. I'd want to make it, say, $9. You don't want to make it too extreme because nobody's going to play it in that situation, right? And you don't want, most people aren't figuring out the expected value of their game, so they're never going to actually figure this part out anyway. But you want it as close to that as possible to get people enticed to play it. So in this situation, as it is now, the -20 probably is going to prevent people from playing, right? Because I already gave you $10. I'm not giving you another 20 after I lose, right? So I probably don't want that to be a -20. Probably want that to be a 0. Well, now if I took that away, now I'm above $10, right? Because if I had those three up, I'm now at $13.33. So if I change this to $1 and $5, but I change this to, say, well, we can leave it at 50. Now, what's it at? $9.50. So if I have a chance to take a $10 and this one and roll a die win $50, people are probably going to play this game. But now, every time you play, I'm walking away with 50 cents, in essence. So over time, you're losing money. But you're not losing enough that you'd actually realize it. Right. It's a little bit here, a little bit there. So you're going to keep playing, and I'm going to keep winning. That's the essence of a casino. What's the worst game to play in a casino? Well, yes, every one of them is actually worse, bad for you. But that wasn't my question. What's the worst one to play? The slot machines are the worst. What do most people play? The slots. Very simple to play. Colors, lights, sounds. All that matters. All that entices you to play. It used to be that when you walked in a casino in Vegas, that you would always hear coins dropping. So now you go to a casino, there's no coins at all. Like it used to be when you put the money in and rolled the thing, you'd actually put coins in it. You pull the things, and coins would fall out the bottom. Like you get quarters, nickel, whatever you're playing. Most of the time they were quarters or dollar coins would come out. You'd always hear, now it's all a card, a ticket, but you'd always hear coins clicking in the bin. Because if you walked in a casino and it was quiet, nobody's winning. Why would I want to play? If you walked in and you always heard coins dropping, people are winning. I'm going to play. So the best time to play at a casino was in the middle of the night when nobody's up. Or first thing in the morning when everybody's still sleeping in Vegas. Because there's not a lot of people playing, but that rule still had to come into effect. You still had to hear people winning. Now, they can make electronic sounds and it doesn't make a difference anything. So it's even worse now than it used to be. But that's how casino games figure out the thing. It's that simple. It's literally just expected value. It's a weighted mean. And as long as that number they come up with at the end is less than what you're betting, they win. Go back to the roulette game. That's where those two green numbers makes their expected winnings better for them. That's their piece. Because that means all their odds aren't going to equal exactly what they're paying out. That's how they keep their expected value down below what you're betting. All right. Let's do a couple other pieces and then we're done. Is this a probability distribution?
No,
Why?
it doesn't add up to one.
Correct. It adds up to more than one. 1/3, 2/3, 1/3. That's more than one. It's 4/3. This is not a valid probability distribution. Is this a valid probability distribution?
Yes.
Why? Okay. It adds up to one. All right. So this is looking at how many times a critical care helicopter is used at the hospital. So we would want this to be 0 because that means nobody's getting killed or hurt, which would be a good thing. I'm just plugging the numbers into the Statology to get the other calculations so you can do those. So in this situation, the hospital is looking to determine if they should get their own helicopter. All right, so the first question says, find the average number of times a helicopter is used to transport the critical patients. So that would be my what? How would we find the average? What did we call average in this section? Expected value. I'm just going to multiply these and add them together. Okay. So there's my mean, standard deviation, and variance. So my mean is 2. Standard deviation is 1.3, and my variance is 1.84. So it varies by just over 1 each time. So what's the probability that the helicopter will not be used at all during a month? 15%. What's the probability that the helicopter will be used at least once during the month? What is it?
5%.
It says at least once. So, well, we just figured out that 0 is 15%, right? It has to add up to what? 1 or 100%, right? So what's left? 85%. Remember the complement? It's easier just to subtract that from 100 than to go back through and add them all up, but you get 85%. What's the probability that the helicopter will be used at most twice during the month? At most twice. 69%, yes. Because we'd add the 0, the 1, and the 2. Should the hospital buy the helicopter? Yeah. So get at least that's used at least twice. Normally, like the mean is 2. So 69% of the time you're going to need it at least up to twice. And those rare occasions that you're going to need it more. So we have 3 helicopters in the state. and they vary based on the hospital. So like Lifestar will stay at Bacchus for a while, will go to Hartford for a while, like it's the eastern side of the state. There's one over on the western side of the state too. And there's one in the south part of the state, not Sanford Hospital. So, and they share the cost because it's expensive. And then when you have to take it, they make you pay for it. At least your insurance pays for it. All right, we're done. So you can start to see even like that stuff that we did back in chapters 1 through 4, it keeps coming back. It's not going away. We're just going to apply it to different things. Somebody asked the class at the beginning of class when the next test is. It is on October 30th. Last week of October. So a couple more weeks.